Right, hello guys. Hopefully this is the last time we're going to have to do it this way, and hopefully I'll be back tomorrow. But I want to at least keep you moving forward. I know you've worked on at this point factors affecting reaction rates, potential energy diagrams, and then we're going to cover today kind of how we express reaction rate in terms of various reactants and products. I think you guys will be able to handle this without me being there. I'm going to give you a couple other videos too to watch. And then hopefully I'll be back so that we can kind of go over all of it tomorrow together and then also start on differential rate law, but we'll see if we get there. All right, so rate of reaction is just measuring the changes in concentrations of reactants or products per unit of time. In general, when we have a forward reaction, the concentration of the reactants is going to go down as it gets consumed, and then the concentration of the products is going to go up as they're getting produced. They have this similar shape, but they're inverted relative to each other because the products are going to appear at the same rate as the reactants disappear in a 1-to-1 ratio. Keep in mind, if you have a different ratio, then we're going to see the curves change a little bit. When we're talking about rate right now, it's not a constant. It's going to change with time as the amount of reactants and products in the container change. So for a general reaction of reactant A making product B, we'll see that we'll look at the change in concentration over A over change in time, which is kind of the final, if we look at kind of our final time, our initial time being T2 minus T1, then we would have that concentration of A at T2 minus the concentration of A at T1 to give us a change in the concentration over delta T. Now, since A is a reactant, we plug in this negative in front of it because it's going to be decreasing. So that's one big thing you'll see is as we talk about and express this for reactants versus products, that will be a difference. So because these are 1-to-1, we'll see that if we express the rate in terms of A versus if we express the rate in terms of B, with B being a product, it's going to increase. So we'll have that positive sign out in front. Our units is going to be in molar per second, which we know molar is moles per liter, so it would be moles over liters times seconds. And here's a whole bunch of different ways that you could see that. You will every once in a while see just a mole per second in terms of some practice problems or videos that are out there. But for the most part, we're going to try to keep it in molar, meaning molarity per second of time. So in general, like if we have that reaction of A to B, determine the rate if the concentration of A changes from 1.2 to 0.75 over a 125 second period, which would be our delta T. So just remember it's going to be that final concentration minus the initial concentration, which will make sense now why we have to plug in that negative out there, because you're going to decrease the concentration, which then gives us overall this positive rate of 0.0036 molar per second. Just some terminology that you should have, and I tried to give you this chart already drawn in on your packet, so if you can just copy down these definitions. There really is a difference between like our average rate, an instantaneous rate, and then the initial rate. So you can think the average rate is basically the difference or the change in the concentration overall between 2 points in time as an average. An instantaneous rate would be basically what's the rate at that particular point in time, which you could get it by taking the slope of the line tangent to a curve at any point. And then your initial rate is just kind of initially what is that at time zero, what is that change in concentration over time. So this avoids complications of if we have like a reversible reaction if you take the initial rate. So just be aware of each of them in the practice problems for homework. You'll kind of go back to that. So our relative reaction rates basically uses the coefficients, and it's when we talk about relative, we're talking about the terms that relate each other in the context of a given chemical system. So we're really looking at the coefficients here of how they're all going to relate together. So for like one example up top here, I'm going to pull this down a little bit. With this one, they're all 1-to-1 in the reaction. So we're going to see that they're all 1-to-1 when we talk about the rate. Now this rate is the rate of the reaction, and then each of these is the rate of that individual species in relation to each other. For many reactants and products, they can disappear and appear at different rates based on them not being in a 1-to-1 ratio. So like for the top reaction, I have the chart over here. You can see the curves are basically just inverted of each other because of the C2H4 being in a 1-to-1 relationship with O2. So as the C2H4 concentration decreased, the O2 concentration is going to increase just as fast or at the same rate. However, if we look at this reaction producing hydrogen iodide, it's not in a 1-to-1 ratio. So for H2, as that decreases, HI, for every one H2, it's going to make 2 HI. So we would expect that if we compare the HI rate, it would be double or twice as fast as H2, which again, if you think about the reaction and the relationship, that makes sense. So one thing is being able to express the rate in terms of a specific reactant or product. So for example, if we look at that synthesis of hydrogen iodide, if we refer to the changes in the iodine, in hydrogen iodine to the change in H2, we're setting this basically equal to like 1/1. So if this is our rate, and you can kind of think of it as 1/1, how does that relate, or how do the other materials relate to that? So since H2 and I2 are 1-to-1 in the reaction, it would be the same for I2's concentration changing over time. However, when we look at HI, think about the fact that if this is 1-to-1, we would expect that in order for these to be equivalent, we would need to take 1/2 the rate of HI increasing over time. If we then change it around and set our initial expression in terms of HI, we would expect that if that's the rate, in order to get these guys equivalent, okay, those values equal to each other, we would have to take that change in H2 over change in time and double it in order to make it equal to this one. There's another video that I'm going to post right after this where they just simply use stoichiometry, which I think for some of you guys might be a better way to kind of think through this. So make sure you also look at this one. But I'm kind of just right now following along with how the book has always gone through this. So in summary, for these reactions, when we set them equal to each other, we can use their coefficients in order to express them in terms of each other because of that mole-to-mole relationship. So let me take you through a couple of practices that are going to be similar to what you're going to see in the textbook. And I'm sorry to just kind of throw these answers all at you, so make sure you actually take the time not just to copy them in, but to kind of think through where the numbers are coming from. So for this reaction, up here for number 1, we're going to express the rate in terms of each component, so we're simply just using their coefficients and also recognizing where we have reactants that are decreasing versus products which are increasing. So if I have the rate of the reaction, and again, think of the rate of the reaction as 1, that's 1. So if I'm going to get the rate of my change of the pH3 over time to be equivalent to the rate of the overall reaction, I would have to take 1/4 of it because of the 4 moles of the pH3 that are being involved. And then that would be equal to the positive amount of 1/1, or 1 of the change in the phosphorus over time. And then that would be equal to a positive 1/6 of the change in H2 over time. And again, it has to do with that idea of how we're relating this to one reaction of it in a way. So then for 2, it's very similar. You can see how it's set up the same way. I just had to balance the equation first. Remember to always check. And then again, making sure the negatives there are with the reactants and our positives are with our products. So how can we actually then use that to make a calculation? So in B, under number 2, it says, how fast is the concentration of oxygen decreasing when the concentration of nitrogen monoxide is decreasing at a rate of 1.60 times 10 to the -4 molar per second? So we can choose to just, because O2 up here is already 1-to-1, we can actually just pull this right out from there. So I'm going to take my concentration of O2, my concentration of NO, and plug it in down here. So when I set this up, and again, because of how I'm having to show this to you, my steps might look like they're missing. I set this initial first part up. I'm just setting the 2 species equal to each other based on their ratio. And then I'm going to take this 1.6 times 10 to the -4 meter per second. That's related to NO. So one little thing, and this negative there I think is hard for students to make sense of. So you can almost think of really just getting rid of this negative over here and bringing it over to the NO side. But really I'm plugging that in for this part of the reaction. That's the rate there. And it just happened to be that in order to clean it up, this negative went over here. So this would go right into there. and then times the 1/4 to give me the rate of O2 that's decreasing. And again, the negative there canceled out. So for this one, and you'll see some textbook questions like this, it gives you the expression in terms of the changing concentration with time for each substance, which then allows you to write a balanced equation for it because of how we set that up. And then for the calculation, when the concentration of H2O is increasing at a rate of the 2.52 times 10 to the -2 molar per second, how fast is O2 decreasing? So with this, I'm going to take out the two components from the equation. Right? Then I'm going to, in this case, get rid of this 1/5. I'm going to multiply both sides by it. I'm going to plug in the rate that was given in place of this concentration of H2 over change in time. And then if I take 5/6 of it, then I will have my rate that the O2 is decreasing. And again, please watch the video that I'm going to post right after this, because I think the way that they're doing it with stoichiometry will help make this a little bit more sense for some of you guys, especially because I can't be there, and try those out. And then you're going to try out the questions on the next page. I put these textbook questions right on the next page of your packet to try out, and then I'm going to post this key so that you can check over your answers. And again, just do your best with this. I know I'm not there, but use each other to see if you guys can start to figure this out, because again, we don't have a lot of time, even though I've been out sick. So good luck, and hopefully I will see you guys tomorrow.